We're going to add 4 more tests today. They will be not on this quiz, but they each all kind of build on each other. Each new test comes because we answer the question, but what if, right? But what if? So we started with the nth term test, and then the question is, but what if it's inconclusive? We need something else. And then we moved on to geometric test. Okay, well then what if it's not geometric? Okay, well then we move on to the ratio test. Okay, but what if it's not positive like the ratio test needs? Okay, well then we add the absolute values. Okay, now what if? So we've got all of these different things that require, and these are the new ones you're going to add. So if you want to put those into your Google Sheet, the first is called the integral test, and they all build on each other. And then you have what's called the P-series test, and then you have the harmonic series test, which I should have added the word test, but I didn't, so go ahead, and then the alternating series test. We're going to start with an example where none of our 3 previous tests work. The nth term test. We take the limit as n approaches infinity of the term 1 over 3n plus 2. We get 1 over infinity, which we get to be 0. And all the nth term test tells us is that we want to not get 0. And when we do get 0, it's inconclusive. All right, we move on to geometric test. We give that a try. What's the clear and present danger? What's the problem with this? It's not geometric. So can't use that. All right, so then we go to the trusty ratio test. All right, well, we'll try that. Well, what if I do the limit as n approaches infinity and I go 1 over 3 quantity n plus 1 plus 2 and then 3n plus 2 over 1, and I try and figure this out. So that's going to give me the limit of the quantity 3n plus 2 in the numerator and 3n plus 5 in the denominator, which is infinity over infinity, but which L'Hopital is going to say it's going to be 3 over 3, which is going to be 1. And that's the one thing that we can't have the ratio test be. The ratio test can't be 1, because if that is 1, then that is also inconclusive. So none of our previous 3 tests were helpful in determining whether this series converges or diverges as a sum. All right, so bring on your 4th test, which is called the integral test. So the integral test has a couple rules in it. The main rules have to do with positivity again. We've seen that before, but they also require continuity and decreasing. By decreasing, they mean each term is smaller than the term before. It doesn't have to decrease to any particular value, it just has to be going down, so it has to have negative slope. So we have to be continuous, we have to be positive above the x-axis, and we need to have negative slope. So you can think of decreasing as something that would have negative slope. If those are all true, then you can swap out the integral for the series. And what will happen is if the integral comes out to be a number, a constant, then the series converges. It doesn't converge to the same constant, but it converges. If the if the integral turns out not to be a constant, then the series will diverge. So the property of how the integral behaves can prove how the series will behave. So they either both converge to a constant, not the same constant, they just converge to a constant in their behavior, or they both diverge. So this is a sample that would satisfy that. So you kind of go through and you ask yourself, is this continuous or not? And this is continuous except for what number? What single number would make this thing not be continuous? Negative 2/3. But my series doesn't start with that. What does my series start with? 1. So I'm fine. Okay, so the domain of that is fine. It is continuous. There's nothing within 1 to infinity that would be a problem. You want to double check if it's positive, and it is. We'd never be able to produce any negative values. And it has decreasing slope. It's negative slope, so that it would be decreasing. How do you know that? Well, hopefully you know that this is a hyperbola in shape. And the hyperbola in shape has branches that are at least decreasing on this side of it. So if you can picture this graph and this part of the graph that comes down like that. So that section of the graph has negative slope, so it's decreasing. So therefore, I can do the integral test, since none of the other ones worked. So the integral test says switch this to an integral. So find 1 to infinity as an integral over 1 over 3n plus, or 3x plus 2 relative to the x-axis. Now, according to chapter 8 that we just did, this is what's called an improper integral. So we swap out the upper bound. So this would be 1 to b instead of 1 to infinity as b approaches infinity. And we're going to have 1 over 3x plus 2 dx. So then we find the antiderivative instead. All right, Alex, do you remember the antiderivative of 1 over 3x plus 2? Mm-hmm.
3x plus 2 divided by 2.
Good, it's a natural log. Yeah, so it's 1/3 of the natural log of the absolute value, let's not forget that, of 3x plus 2 plus c as a quantity. And we're going from 1 to b. So that's going to give me 1/3 of the natural log of infinity minus 1/3 of the natural log of 5. Now the natural log of infinity is infinity based on how the natural log function goes. So the result of this integral is infinite. So since the result of the integral is infinite, then that means the series doesn't converge to anything. So the series must have divergent behavior. So that's our conclusion. Therefore, the series of 1 over 3n plus 2 as n goes from 1 to infinity is divergent. So as the behavior of the integral goes, so the behavior of the series will go, as long as the integral met the 3 conditions: continuous, positive, and decreasing. So, Rain, this kind of gets to your question when they talk about conditionally convergent. That means, or that if we would have gotten conditionally, we would say it's conditionally convergent because it met the conditions of the beginning that are required. To be they say, what conditions did it meet? It met the conditions that it was continuous, positive, and decreasing. Okay, so it's just meaning that you've checked the for integral test. Okay, so each of these tests gets more and more restrictive. Remember that the ratio test, the only condition is positivity. The integral test has 3 different conditions: continuous, positivity, and negative slope or decreasing. And then as we add like the p-series test and alternate, like they're going to have more conditions. So each of them adds in. That's all the conditionally convergent means. okay, that you continue to add conditions. Okay, so let's try another one. Does this series converge or diverge? Okay, well, I'll tell you right away that it's gonna, all of these are gonna be fine. It is continuous. It does have all positive values, and it has a negative slope, so it's decreasing. So all three of the conditions are met. I'll also say the ratio test doesn't, or the nth term test is inconclusive, the ratio test is inconclusive, and it's not geometric, so the geometric test doesn't apply. So assume that you've already thought through all of those things. So then we want to consider what would the integral do. So we're going to apply the integral test. So I want the integral from 1 to infinity of rad x over x cubed dx. So we're going to replace our upper bound again. But I'm also wanting to simplify, because x to the half over x cubed is the same thing as x to the half multiplied by x to the negative 3. So as I evaluate my integral, I want to simplify before I think about doing an antiderivative. One thing that the habit that a first-year student in calculus, I'm really trying to break their habit, is they want to take this equation, the x to the half, and they want to do an antiderivative just to x to the half. Then they want to do a separate antiderivative just of x to the negative 3, and then group them together after. And I keep having to break their habit. There's, in multiplication with integrals, you can't do that. You have to consolidate the x to the half and x to the negative 3 first before you would think about doing any antiderivatives. So we're going to have to say, all right, when I put them together, it's x to the, okay, and what consolidated power do we have? It's negative 5 halves. Okay, it's just adding the powers together, and so I get negative 5 over 2. You have to consolidate them together first, then you can do your antiderivative. So my antiderivative on x to the negative 5 half is going to be x to the negative 3 halves times negative 2/3 plus the constant c, all going from 1 to b. All right, so then we can substitute our bounds. So this would be negative 2 over 3, there's my negative 2/3, and then times infinity to the 3 halves, and then plus 2 over 3 times 1 to the 3 halves. So by plugging infinity into the first part, we're going to get 0, and then plus 2/3. And so I get the constant 2/3. So since the integral test turned out to be a constant, it tells me what the series will do. So therefore, the series of rad n over n cubed is convergent. Please don't make the assumption that it's convergent to 2/3. That is not what we're saying. The area, that's what an integral means. An integral means the area is converging to 2/3. But since the integral is converging on a constant, then the series has to be convergent itself. But those two things are not equal in the number, yeah?
Will we ever need to find where the series converges?
No, not unless it's geometric. And the geometric has that S formula that we use, a sub 1 over 1 minus r. That's the only time. All right, so the integral test leads you to something more specific, a general called the p-series test. The p-series is when you can consolidate all of the powers. And so that's exactly what we just saw, where we consolidated all of the powers down to be a particular power of x. So we got x to the negative 3 halves. So the p-series test is your next one on your list. It has the same 3 conditions. It has to be, because it's coming from the integral test, it has to be continuous, it has to be positive, it has to be a negative slope. If you can consolidate all of your powers, and if your powers are greater than 1, P just stands for the word power, so it's like the power series test or the P series test. It will converge if the power is greater than 1. So this is the opposite of like a ratio test. A ratio test says it will converge if the ratio is less than 1. But here, it will converge if the power is greater than 1. It will diverge when the power is anything less than 1. We'll have divergency. Okay, what's the obvious miss here, or what's missing? What about when P equals 1? That'll lead us to the next one that we need. Okay, but this is the P series test. Okay, so it comes with, all right, so if you're doing this here, so will this series converge? All right, well, we've got continuity, because the only place of discontinuity would be 0. It's always going to be positive, and the negative slope is going to be here. So you don't have to go through all of the limit stuff. You just have to rewrite this as n to the blank. All right, so this would be n to the 3/2. And so you don't have to, like, it saves you time. Just like in a geometric series, if you can see that r is less than 1, you know that it's going to converge. In a P series, if you see that P is greater than 1, you know it's going to converge. So you don't have to do any of the proofs. You can just say, since the conditions of the P series test are met, and since P equals 3/2, which is greater than 1, then the series will converge. Okay, if you happen to not remember the P series test, you can always do the integral test, because it's going to be the same thing. The P series test just saves you time without having to actually go through the process of doing the integral. You can just cite the conditions being met and check the value and then move on. So it's a faster way, just like geometric series. All right, so we move on to the next need. So we've got our P series test now. So the logical next question would be, what happens when P equals 0? Excuse me, when P equals 1. So that's what comes next. So that's our next limitation. So we've gone through, we added pretty quickly, added the integral test. A P series is part of the integral test or logically follows from that. But then we have, okay, we got to deal with P being equal to 1. All right, if a P series is what you call that, then when P equals 1, this has a special name. It is called a harmonic series. It's a special name when P equals 1. So, okay, like right here, we understand that there is a 1 right there. So what's going to happen there? All right. Well, we can go back to, is it going to diverge or is it going to converge? Does it meet the requirements of the integral test? Can I use the integral test to do this? Okay, where would it be discontinuous? At 0. Where would it be, or is it ever going to be negative? No. Do the terms decrease? Does this have negative slope? Yep. Okay, so we could use the integral test. What would the integral test say? What would I get as my integral? I get the natural log. Okay, the bounds would be 1 to infinity. So I plug infinity and 1 in. I get natural log of infinity, which is infinity, which means it diverges. Okay, great. All right, so according to the integral test, the harmonic series, the special condition, will diverge. And again, now, every time you see the harmonic series, you can say, oh, it's a harmonic series, it diverges. You can just claim it as long as it meets the conditions, because it meets the conditions of the integral series test. But I saw cool proof. You don't have to know this. I just think it's really interesting, and I want to show you. Yeah.
Why would you just say the P-series test diverges if it's less than or equal to 1?
We're gonna need a special case of the harmonic series for the fourth and final test, which is one final situation. Okay? Yeah.
So as whatever power n is, like that's p, like regardless of what the numerator is, or if it's like 2n or 3n, it's just like whatever's attached.
Okay. Yeah. So if the numerator is a constant, you're gonna pull that constant out to the front so that you get 1 over.
So it has to be 1 over. Is it, if it's like 1 over 2n, is that fine? Or like,
Well, the 2 would get pulled out to the front.
Yeah. Okay. And then.
It's got to get to the form of, it's kind of like a u substitution. Like every natural log you want to be in the form of 1 over u, so you replace the whatever the denominator is with u so that it gets to that form.
So it has to be 1 over.
Yep, yep. All right, I just think this is cool, so I'm just going to show it to you. I'm never going to test you on it, I just want to show you. All right, what does 1 over n, what are the terms of 1 over n? Like, give me the first, I don't know, 8 terms. What would it be? What's the first one? 1, okay, then plus a half, plus, hang on, I'm just gonna, next 1/3.
So long ago. Never mind. Like, that was so long ago.
Okay. All right, so this is what the harmonic series is. At its face value, it's not clear that it diverges. It's just a series. You just keep adding. All right. Take, keep, say it as a keep. Keep every term that's a power of 2. Okay, keep every term that's a power of 2. So what terms would we keep? Which terms are powers of 2? 1 is a power of 2. What power is it? 2 to the, okay, what else? Keep 1/2, that's 2 to the negative first. What else would we keep? Okay, what else would we keep? 1/8 would keep, okay. All right, for all of those terms, replace what we're not going to keep with a power of 2 that was smaller than it. Oh, let me put those back a second so we can see. Okay. No.
I'm trusting.
Trust me. The fraction 1/3. What's the next fraction that's directly smaller than that? 1/4, right? Is it 1/4 is direct, just small, it's smaller. Okay? Do you guys have, if you bake, you have those measuring cups? And they all fit into each other, right? So you have a 1, and then a 1/2 fits in that, so it's smaller, and then a 1/3 fits into that, and then a 1/4 fits into that. Yes. Okay, so if I replaced 1/3 with something smaller than it, so I replace it with 1/4. Okay, now 1/5, I want to replace it with something that's smaller than it, but I'd really like it to be a power of 2. So what's 1/8 would be the next one. And I do the same thing to the 1/6, and I do the same thing to the 1/7. So I'm going to, how many 1/8 are there now? 4 of them. How many 1/4 are there now?
2.
Okay, and a half. Okay, what would come after the 1/8 that I have that I kept? What would have come there? It would have been a 1/9. Would I keep that 1/9? No, what would I replace it with? 1/16. And then I'd replace the 1/10 with 1/16, and then 1/16. So how many 1/16 will I have? I'll have 8 of them. All right, now, because I'm replacing them with bigger or smaller terms? Smaller terms. So overall, the result would be smaller, right? Because everything is smaller than what I put in. All right, so the original series, so now I've got 1, and I have a 1/2, and I've replaced the 1/3, and then I've got my 1/4, which is original, and I have all these, and I'm keeping that 1/8. Then I'd be replacing a 1/16, and another 1/16, and another 1/16, and I'd have all of those. Okay, but in relationship to each other, it's like this. It's no longer equal. What I started with is larger than what I have. Okay, and then I heard some of you say, okay, like how many 1/4 are there? 2 of them, which is really, okay, and then how many 1/8 are there? Which is really a half. And then how many 1/16 are there? 8, which is really a half. All right, so then I have 1 plus a half, and then it would be these 2 terms combined to be a half, and then these 4 terms combined to be a half, and then these to be, well, those plus after the dot, 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 that would be a half. All right, so if I start with the number 1, and I continually add on a half, and then another half, and then another half, and another half, eventually, what direction is that sum going? It's getting to infinity. And if what I start, so this is infinity, but the original one has to be bigger than that. So if my smaller one is already infinity, the bigger one has to be bigger than that, and it must be infinity as well. So to infinity and beyond, right? So by virtue of the fact that this one diverges, the thing that's larger than it must diverge as well. And we actually did that as a theorem in chapter 8. We said if any sum A is smaller than any sum B, and if you can show what about sum A? Sum A diverges, it forces the other one to diverge as well. Because if the smaller one diverges, the thing that has, in order to be larger, it must diverge as well. Anyway, I saw all that when I was, my Google search just took me to this, and I thought, all those powers of 2, and I thought that was cool. I'll never test you on that, but I thought that was really interesting. Okay, last one. Okay, here is your last and final special case. This is very similar to the harmonic series because it has the 1 over n. So Rain, you were asking about that. Does it have to have 1 over n? Yes. But what else does this have that makes it slightly different? And what is that going to do? Okay, alternating. So the inherent problem, okay, well, let's check our things here. What's the first check? Is it continuous? And the answer is yes. Okay, but what's the next check? Is it positive? And the answer is it is not positive. So the inherent problem is that we don't have positive terms. Okay, sad. All right, so what do we do when we don't have positive terms? All right. Oh, we don't have all positive terms, we should say. We don't have all positive terms. Okay, it starts out positive. It's the number 1. But the next one is minus, and the next one is plus, and the next one is minus, and the next one is plus, and the next one is minus. Okay, so we have some positive terms. Half of them are positive, but the other half are negative. Okay, so if we know that a harmonic series will diverge, what about an alternating harmonic series? What will that do? Okay, so your last thing is that an alternating will converge. Okay, if, these are the last conditions we have to meet. The first one says, aside from the -1 n plus 1, each individual term is positive. All right, what does that mean? That means if you took the -1 n plus 1 out of it, just to look at it, would everything else left still be positive? Okay, if that thing wasn't there, impacting, or is there something else that's creating negativity besides? So if the only thing that's creating the negativity is the -1 to the n plus 1, all right, that's good. Are all of the terms still decreasing? That would be good. We could meet that. And then the final thing that is key is as they decrease, they have to get small enough to where they're approaching 0. They can't just be leveling off and decreasing towards some other random constant. It has to be 0 as your final part. So that's the last condition. So aside from that, would you have all positivity? And are the terms decreasing in such a way that they would eventually get to 0? In other words, if you focused on the limit, would the limit approach 0? So this is called the alternating series test, and it's the only way a harmonic series would converge. Harmonic series in every other way will diverge unless they are alternating. And if it's an alternating harmonic series, then it will be the only one that converges. So when you see a spot, an alternating thing in there, anytime you see that -1 to a power, you should like hone in right on that and be like, beautiful. I see alternating. So if the other 3 things are all true, I have convergence, which I would never have in a regular harmonic series. I would only have it in an alternating harmonic series. Okay, so this would be this case. We would consider this separately. So considered separately, number 1, all terms are positive. Number 2, all terms decrease. And number 3, the limit as n approaches infinity of all the terms is 0. Those are the 3 conditions for alternating harmonic series. So this series will converge. It's the only harmonic that will converge. Every other harmonic will diverge. So the conditions of convergence are met. Okay, you've met all the requirements. In my head, I sort of picture the Captain America scene at the beginning. You've seen the Captain America movie. Okay, Steve Rogers is trying to get into the army. And he goes and he keeps getting rejected because he's not meeting his eyesight's bad, he's puny, he's underweight, there's something wrong with him every single time. So he just keeps rejected. But finally, once he meets all those conditions, he has the injection of the serum, whatever, they go through the beta ray thing, whatever. Okay, now the conditions for him to be Captain America are met. Same thing here, you just got to meet them all, otherwise you reject it as divergent. All right. We will save this last one. I'm working on, This is not in the final form. I think by the time I get to Tuesday, I'm still not satisfied with this. I'm trying to come up with a good flow chart. If this, then that, to like put it all together. So I'm almost there, but I'm not 100% satisfied with this one. So I'm going to keep working on that for Tuesday. All right.